Okay, hi everyone. So this presentation is about Java build tools. So the motivation for this talk is that although Java is known to be very performant, very easy to learn, and have very good IDE support, Java build tools like Maven or Gradle aren't always as good as the Java language itself. So this talk will have 4 sections. We'll talk about why Java build tools are hard from a user perspective, or at least harder than you might expect them to be, given the Java language. We'll talk about why Java build tools are hard from an implementer perspective, like why doesn't someone just go and make a better build tool that everyone can use. We'll talk about Mill, which is one of my own personal open source projects that tries to explore this problem space and see where we can improve upon it. And one of the key ideas behind Mill, which is object-oriented builds, which allows us to greatly simplify the way someone defines and uses a build tool so it's not so confusing and complicated. So about myself, I've been programming since 2004. My first language was Java. It's been 20 years. I've been working on open source projects since about 2012. My last job was at Databricks, which is a big Scala shop. So a lot of these projects are Scala on the JVM, but also a lot of Java and other JVM-related technologies. My professional expertise is developer tools. So everything that happens before your code goes to production, I've probably worked on, like CI systems, build systems, testing systems, ID integrations, all sorts of remote dev environments, and so on. So the first part of this talk is why I build tools hard for users. So I assume everyone here uses Maven or Gradle or something like that, right? Like this is a Java meetup. So from my experience, the main complaints people have about tools like Maven or Gradle is the performance, ID support, and the ease of programmability. Basically everything that Java is good at, Maven or Gradle aren't often as good. So for example, from a performance angle, everyone says that Go compiles quickly. No one talks about how Java compiles quickly, but Java actually does compile very quickly if you get into the meat of it. So for example, if you look at the Netty code base, this is a popular open source networking client-server framework. It's about 500,000 lines of code, not a small project, 50 sub-modules and thousands of files. Clean compiling the whole thing takes about a minute or so. And I can show you this live if I copy-paste this into my terminal. We're not going to wait for it. We'll come back later. Yeah. So you take my word for it. It'll take about a minute to clean compile the whole of Netty. And this, without tests, without linting, 10 cores parallel on my 10-core MacBook, all the normal things. So if you compile a single module, just using compile instead of install, you get similar kind of performance. So although install does some things that compile doesn't, and there's some parallelism that compiling a single module doesn't get, in the end, you're still looking at a few thousand lines a second. So for a single module like Netty Common, which is about 30,000 lines of Java, it takes about 4 to 5 seconds to compile clean. So this isn't particularly fast. Like people talk about other languages where you hit compile and it's already done, or scripting languages where you don't even need to compile it. What most people don't realize is that if you take Netty Common and compile it outside of Maven, it takes 1.5 seconds instead of 4.5 seconds. And this is actually the exact same command that Maven prints out to the terminal when you run Maven compile. Like it's what Maven's doing, just without all the overhead around it. And this overhead around it just to check, do all the build tool things. And if any of you experienced at working with Java and the JVM, you'd know that running a JVM program like this from the command line cold is like the worst possible performance you get out of any JVM application. And the Java compiler is written in Java running on the JVM, so that applies to this as well. So the way you run JVM applications, you keep them warm, you let them get optimized and warm up, you avoid a cold start, or at least amortize a cold start over many usages. And if you do this for Netty Common, you'll find that it runs about 5 times faster than it did cold, and about 15 times faster than it did when compiled within Maven. So this is still a clean compile. I'm not skipping any of the work, but it just shows that, although Maven's what everyone uses and it feels kind of slow and clunky, it's not actually Java C that's slow and clunky. It's kind of just the build tool wrapping it. This is actually the exact same Java compiler, same Java version, same source file, same dependencies, and somehow it's 15 times faster without having to rewrite it in Rust or something like that. So Going back to the demo, you'll see that in this case it took about 54 seconds to clean compile the whole code base. If I run the single module compile, it'll take about 5 seconds after cleaning. About 174 source files in netcommon, 4.5 seconds, similar to what we saw on the slide. If I just run Java C raw, just with this very long class path that you're probably not going to type out yourself, you see it takes about 1.3 seconds here, so about 3 times faster than what we saw in Maven for same class path, same source files, and same Java compiler. And if you run it in memory, like without getting it to allow it to warm up, you'll see it starts off a bit slow and ends up getting faster and faster. You see this duration here keeps going down as the Java, as you know, the JVM warms up, gets optimized, everything, all the good stuff. And after a while, you see it's taking about 300 milliseconds or so to compile the same 29,000 lines of code that with Maven took about 4.5 seconds. So just to look at this, how I'm doing this in-memory benchmark, it's literally just a small Java application with a main method. And all it does is it has a while loop that calls the Java compiler in memory over and over. So it's a clean compile still. We are not caching any of the compile class files. We're just keeping the JVM around so it's a chance to warm up rather than starting cold every single time. So compiling Java is not the only thing you do in your day-to-day work, but this is just a demonstration of how much overhead your build tool can add over what's actually a very fast underlying tool chain. Like, unlike Python or unlike Ruby, Java actually does perform very well if used correctly. So we don't need to rewrite the compiler in Rust in order to get good performance out of it. You just need to make sure you keep it warm and manage the compilation correctly so you don't have tons and tons of overhead wrapping it. So that's the performance angle. Next thing I'm going to talk about is IDE support. So Java is famous for having good IDEs. Java build tools also have IDE support, but it's often not as good as you'd expect given how good the Java experience is. So let me go to the demo. I think it was this one I wanted. Okay, yeah, it's this one. Okay, so this is a checkout of the Mockito code base. So you all probably know Mockito is a popular open source unit testing library. It's built using Gradle, uses the older Gradle Groovy syntax rather than the newer Kotlin syntax. And you'll see that we do have support for Gradle in the IDE. You do have syntax highlighting and you can jump to definitions and things. But when you try to jump to things, often the result is not as useful as you'd hope for. For example, when I jump to JVM args, I get this getter, I get this setter, or two setters, and what I don't get is any information about what was there before I set the value and where the value is going after I set it, like who's using it, what it uses and who is using it. It's all kind of just a black box still. And it's not just JVM args, but you jump to any of these things in Gradle, you'll see that you just get these stubs. So you have a type signature, which is useful. If you set up the sources, you can also get the doc comment. But you don't get all the good stuff that you'd expect from IDE experience. You don't get find usages, you don't get jump to definition, you can't like recursively search up the implementation to see what it's doing. It's kind of just a very shallow, anemic experience. And this is in comparison to you open up some random module or some random file in the actual Java code base, and you'll see that any file in this code base, even if I don't know what it's doing or even if there's no documentation, I can jump to it and jump to it and jump and kind of recursively jump around, not just the code in this library, but also the code in upstream third-party libraries and the code in the standard library. So even though, for example, isolated URL class loader builder has no documentation, which is probably the case for most things in most code bases, I'm not stuck because I can jump to it, see what it does, and kind of recursively explore the code base to understand what it's doing. And this is important because usually when you look at a code base, it's because the code base has is doing something you don't want it to do, and you're trying to figure out why this misbehavior or this mismatch of expectations is happening. So easy to do in normal Java code base, basically impossible to do in a build tool like Gradle unless you've already memorized everything and all the edge cases and semantics, which that's what people end up doing. So you wonder why that's the case, right? Like this is the exact same IDE. It's written basically the same language. This syntax is Groovy, but the implementation is in Java. just like the code base we're looking at here in the Mockito. And the answer is that the problem is not the language or the IDE. The problem is basically that most build tools like Gradle are configured using these global mutable variables like JVM args. So you see here we're mutating a global variable, or we're like calling a function that mutates a global variable on our behalf. And just because we wrap the global variable in a getter or setter doesn't make it any less global or any less mutable. So like humans are not good at figuring out global mutable variables. That's why you don't use them in your code, application code, if you can avoid it. And it turns out IDEs are also not good at navigating around this use of global mutable variables. And if you use global mutable variables in your application, you'll get the exact same experience here, where you jump to a type definition and you have no idea where it's being used or who's using it or writing to it, because anyone in the whole code base can be doing so. So most Java applications are written using classes, methods, overrides, super, and so on, which IDEs are good at working with, whereas build tools like Gradle are written basically using a big pile of global mutable variables that IDEs are not good at working with. And that's why IDEs, even though it's the same IDE in the same language, aren't able to provide the same experience in working with your build tool. So that's IDE support angle. I showed you the Gradle Groovy DSL. The Kotlin DSL has a similar problem. The type system for Kotlin does help, but the global variables still pose a problem. And even Maven has a similar problem, where you look at all these Maven XML snippets, and there's no way for you to jump to implementation of what exec does or what property regex does and figure out more. It's basically you have to memorize it or have ChatGPT memorize it on your behalf. So the last thing I'm going to look at is programmability. So every build tool is programmable to some extent. Build tools do a lot of things out of the box, and there are lots of plugins, but you always, any real project, end up having to do things that plugins don't support or don't support quite the way you want them to. Like maybe you need to have a custom Git metadata deployed to production for debugging purposes, so you know what version's running on your server. Or maybe you need to deploy a bill of materials listing out the dependencies for security scanning or something like that. And it's often very bespoke to each company or each code base. Both Netty and Mockito we saw earlier do have these kinds of special customizations. So as a strawman requirement, let's say I want to save the project line count as a tech resource file just for the application use at runtime. So it's kind of artificial and contrived, but it's just representative of the things that people have to do in their build tool. So this isn't impossible using existing build tools. Here's an implementation using Maven, but it can be surprisingly tricky. So there's a bug in this implementation, and let's see if anyone can spot it. So just give you like 30 seconds. Basically, it uses the Maven exec plugin. We add a new phase to execution, or with a new name. We shell out to sh-c. So okay, this doesn't work on Windows because Windows doesn't have sh, but even on Linux and Mac, this won't work properly. And we use mkdir-p, and we use find xargs to try and count how many lines and put in yeah, I think it.
Oh, you're just saving the line count of the last file.
No, that's not right. Well, if you have more than, I think, 32,000 files, it probably will stop working because xargs chunks it, but for most programs, it should be okay.
Is it because you're running in the wrong phase?
It's not.
Okay.
Yeah.
Is it WC word count?
No, this is correct. -L, it counts lines.
Okay.
So the bug here is we forgot to escape our ampersands because it's bash in XML, not just bash. So this is a kind of like stupid, silly, irrelevant thing you don't want to have to care about when you're customizing a build. But it just shows how, even for such a trivial requirement, this is the most hello world customization you possibly ask for. You will screw up and you won't spot it, and your code reviewer won't spot it. It might blow up later unless you have some tests in your build, which you probably don't. So yeah, there are other ways to do this. You have AND scripts, you have custom Maven plugins, but they all have similar trickiness. None of them are impossible, but they are trickier than you expect for such a trivial requirement. Gradle has a different set of trade-offs. So Gradle runs on the JVM. It's written in Groovy or Kotlin. This shows a Kotlin syntax. So instead of having Windows problems, or instead of having bash and XML escaping problems like Maven does, you have other things you need to deal with, like properly wiring up your depends-ons, input files, do last or do first, and so on. So this also has a bug, and let's see if anyone can spot this one. So you can see I override this task, I add a new task process resources. I override it rather. It depends on generate line count, which I registered here. I declare the input files, output files. I use do last here so that after all the other stuff is done, it starts lines at 0, looks at all the source directories that exist, walks them, looks for .java files, reads the lines, counts them, adds them to total, and writes it to a resource file. It prints out some logging.
The total lines, the dollar sign, like that's not going to be called, or will that be called?
Which dollar sign?
Dollar sign total lines in the
Total
print
line.
line, or will that work?
I think that's fine. I mean, this is just logging, so it doesn't really matter.
Total lines out of scope when you use it in write text.
Where? Down here? Nope, I think it looks like it's in scope.
Okay.
Yeah, this looks vertically aligned.
Oh, I see.
Yeah. So the bug here is that we were declaring the wrong folder as input files. So we were declaring too broad a set of inputs, which mean that if you write to if you make a change to source main templates or source main resources or source main whatever else config, it will cause this task to reevaluate even though the output is exactly the same. So it won't make a build incorrect. When you test it, it'll look fine. It'll just be randomly slower sometimes depending what file you touch. So you're almost definitely not going to catch this one, and your code reviewer is not going to catch it. And what's going to happen is it'll slip into your code base, or might slip in indirectly through plugins, which will also have similar bugs. And that's how over time your code base build system will become slow and flaky for reasons no one can really explain, because these bugs are in these build configs are just so hard to catch even for experienced engineers who've been using these tools for years. And this is the most simple hello world like customization. Anything else will be proportionately more complicated and difficult to debug. So that's the user-facing perspective of why build tools can be challenging. The performance, ID, support, programmability, these are all great for Java and not so great for things like Maven or Gradle built on top of Java. So the next obvious question is, why doesn't someone just make a better build tool? Like, if everything's not good, well, make a better one and everything becomes good. And the answer is, build tools are often quite hard to deal with from an implementer perspective as well. It's not easy to make a build tool. It's not easy to make an easy build tool. So every tool starts off pretty simple. This is an example of JBang, which is a small command line tool that lets you run Java, single file Java applications, where you just put a comment at the top saying what libraries you want, what Java version you need, and automatically just download the right library and download the right Java version and compile and run your code using it. Has anyone used JBang here? It's quite neat. Like it's like you're running Java, something.java, but you can put dependencies and other things. So you're not limited to just a standard library. So JBang is very simple, but for any more complicated tool, you end up having a lot of keys and values. And it ends up becoming quite messy. You end up wanting to put them in some kind of structure or hierarchy, so it's not just one huge flat list. So another example of this is GitHub Actions, which can be thought of as a build tool of sorts, where you're having steps that you orchestrate to build your software. Not quite the same as Maven or Gradle, but same in theory. So GitHub Actions, instead of having a flat list of key value pairs, you have a hierarchy in YAML with nesting and so on. But what you realize very quickly is that it's not just a tree structure, but you end up kind of just passing variables around your YAML file. It's no longer just a hierarchical config. It's kind of like a programming language, right? I'm passing this message parameter to this workflow input parameter that then gets used in its body. I am defining this build job here. I'm referencing it here. I am defining this shared YAML workflow here. I'm inheriting it in these two different jobs, or calling it depending on how you look at it. And when it really comes down to it, you realize that your build tool is, even though it looks like a hierarchy, that what you actually care about is the graph structure. So this example is GitHub Actions, but it applies to Maven, applies to Gradle. When you get to the meat of it, it's really some sort of graph underneath that you as a user are trying to configure to build your software using some predefined templates, like this is a Java module, or this is a Kotlin module, or this is a Gradle VM module, or so on. So the reason why build tools are difficult for someone to make simple is that you need to define some kind of templated graph computation engine. So if I have, for example, 3 Java modules below, each one has an assembly step, each one has a compile step. some of the class paths depend on others, some of them don't. Each one has their own sources. We need a graph because the tool needs some way to know what order to run their steps in and what can be parallelized and what can't. It needs to be, there needs to be computations because class files and jar files don't create themselves. Somebody needs to say this is how you create your artifact, whether it's in Bash or Java or Kotlin or C++ or whatever. And it needs to be templated because the different parts we have built are often very similar, like different modules have similar structures, but not quite the same because some module will have a special compilation post-processing step, some module will have special command line flags and so on. So there are lots of ways to do this, like GitHub Actions does it using, the graph is defined using these needs keys, computations are bash snippets, templating is done using these handlebars, curly braces. Maven, Gradle all have their own similar syntax features to handle all of these things. And some build tools try to put this all in plugins, but that doesn't really solve the problem because if this is complicated, the plugin authors will make mistakes as well, and you end up with buggy plugins rather than your own buggy build. But the end result of your build being buggy doesn't really change. So this makes build tools complicated. Like you end up having to deal with all these concerns, like how do you define custom tasks, how to run things from the CLI, what runs in what order, how you define what a task does, how do they pass data to each other, do you use file system, do you use protobuf, do you use RPC, JSON or whatever. And if you look at any build config, for example, the Gradle build config we saw earlier, which is quite complicated for such a simple task, you'll see that a lot of the complication comes from needing to answer all these questions. So it's not that the Gradle people want to make a complicated build tool, it's that build tools need to do all these things. If a build tool doesn't do any of these things, you will stop using it because you want parallelization, you want caching, you need customizability and so on. So you need all these things. But in providing all these things, you end up having a complicated API. So that's the basic problem of why build tools are so hard to make simple and why simpler ones haven't really come out in the last few decades. So that's why build tools are hard for implementers and not just users. The next section, we'll talk about one of my open source projects. This is called Mill. It's a build tool that explores this solution space and sees what is possible to improve here. And so Mill's an open source build tool targeting Java, Kotlin, and Scala, basically all the JVM languages. The build files are written in Scala syntax, which might be a bit different from the Groovy or Kotlin syntax you've used before, but hopefully it's not too different. Like you have packages, imports, extends, methods defined using DEF, and so on. So it's a small project. There are a few maintainers and committers, definitely much smaller than Maven or Gradle, but there are people using it out in the wild. I know people at Disney streaming and Netflix who use it in their own projects because they've raised tickets with on GitHub. Documentation's at mill-build.org if any of you want to check it out. And using it from the command line, you can say /mill using a bootstrap script similar to Gradle W or Maven W. So /mill, foo.compile, foo.run, foo.test, assembly, and so on. All standard build tool things. So standard build tool things aren't that interesting. Every other build tool does the same standard things. So what Mill does that is interesting is that it tries to improve upon the performance, ID support, and programmability of Maven or Gradle and other tools. So, for example, for performance, in order to compare performance, you need the same project built using multiple build tools. These don't really exist out in the wild. No one wants to set up 2 build tools and keep them maintained over time. So to do this demo or comparison, we took the Netty code base, which is built using Maven, and we, as a proof of concept, just ported the whole thing to Mill, got everything compiling, got all the tests passing, so all the flags and stuff are set up correctly, all the dependencies and stuff are wired up correctly. So everything works, and once we got that equivalently working in Maven and Mill, we can then do some comparisons. So the first thing we noticed is that Mill's a lot faster than Maven was to compile the same code. So the green highlighted section is a benchmark we saw earlier in the terminal where Maven took about 50 seconds to parallel clean compile the whole Netty code base on my laptop. And Mill takes about 9 seconds to do the same thing. So I can show you this to you live. So earlier we saw Maven clean compile, Maven-T10, fast install everything. The equivalent Mill command looks like this. I say Mill clean and time the Mill wildcard.compile, means compile everything. And it's actually compiling the same code, same module layout, same source files. I've gone through the logs and counted all the compiling X Java sources, and I added them up, it adds up to the same number. And it takes 7 seconds instead of 50 seconds. So this is still slower than you expect. Like given the numbers we saw earlier, we should expect it to take about 5 seconds on one core to compile a whole netty code base using Java C. Here we're taking 7 seconds on 10 cores, so it's still not quite as ideal, but it's a lot closer than what you'd see using Maven or Gradle, where you're taking 50 seconds on 10 cores to compile the entire code base. Apart from the clean compiles, incremental compiles are also a lot faster. So if I make a single change and run a compile, it takes like a fraction of a second. So for example, if I go to a random file in netty, where's my netty? It's over here. So I go to a random file in netty common, source main Java, add like hello world as a comment at the end, and run a non-clean compile. You'll see that Mill is able to quite quickly detect that I only need to compile one source, and I don't need to compile anything else in this module, and because I'm not changing any of the implementation code, I don't need to recompile anything in downstream modules as well. So it's pretty fast. Whereas if you try to do the same with Maven, I think we'll be waiting another 50 seconds because Maven doesn't have the same incremental compilation setup that Mill does. So that's versus Maven. Versus Gradle, the numbers aren't quite as dramatic. So Gradle is faster than Maven in many cases if you set it up correctly. Like Gradle does keep the JVM warm in memory with the Gradle daemon. Gradle does have some sort of incremental compilation. So instead of seeing a 4 to 6x speed up, you're seeing maybe a 3x speed up for clean compiles and maybe a smaller 5 to 10x speed up for incremental compiles. So it's not as dramatic. Gradle does, but Gradle does still have a lot more overhead than Mill does. For example, taking 1 second plus to do an incremental compile and still taking 20 seconds to clean compile everything, where Mill takes about 6. So compilation is not everything. There's some other interesting features worth mentioning briefly. Mill supports large code bases quite well, so things like multiple languages, even some experimental support for Python and TypeScript and Android. Large numbers of submodules. Maven and Gradle tend to slow down and when you get to more than about 100 sub-projects or submodules, Mill can get to about 1,000 before it starts having problems. Selective test execution, where if you open a pull request, you can configure Mill to compare the main branch with your pull request branch and only run the tests which are affected by the changes. So that's quite handy to save time and save money on your GitHub Actions workers. And automatic build profiling. So if I run a clean compile with Mill, it generates let me find this. It generates this Mill Chrome profile file automatically for you. So you're not meant to read this manually, but it has a metadata about where every task started and ends. So if this is a format that's understood by Chrome, so if anyone who has a Chrome browser, which is probably all of you, you can go to chrome://tracing, which is a built-in parallel profile visualizer that everyone's Chrome browser has. And if you generate a JSON file in this format, which is documented online if you Google Chrome tracing format, you can immediately see where the time went in my build. So the most common question of any build tool is, why is it taking so long? And Mill makes it very easy to answer that question. So you can see where the build was fully utilizing all 10 cores on my MacBook. You can see where it got bottlenecked in Common Compile stopped, other thing ticked off, started using more cores here. In the end, it got bottlenecked again on Microbench compile. That took a while to run at the end. And this is interesting because even if you know nothing about netty, you know nothing about Mill, if you wanted to do something to improve this number of 10 seconds to clean compile netty, you probably already have some ideas. Like maybe Microbench can be split into smaller submodules that can compile in parallel, so that we don't have this long pole holding up the entire build. So this is not impossible with other build tools, but with other build tools like Maven or Gradle, it's typically a lot more annoying to set up, enough so that you probably won't do it. Like when your build is slow, you're not going to go sign up for Gradle Enterprise, pay for Gradle Enterprise with your credit card, and set up a self-hosted Gradle Enterprise server to get all this just to get your build scans wired up. But with Mill, because we generate it by default on just every command, any command you're not sure why it took so long, you just take the JSON file, dump it into Chrome, and you see where the time went. This applies to compile, test, deployments, and so on. So that's a performance angle, which I think is quite neat. Like, apart from just the raw performance of having less overhead than the existing build tools, better exposing the underlying performance of the JVM. And we also have things like supporting large code bases and profiling and so on. Next, I'm going to talk about ID support. So Mill has ID support just like Maven and Gradle have ID support, but in many ways ID support is much richer and more useful. So if I pull up the demo, so to compare this, I'm using the Mockito code base. So Mockito is built using Gradle normally. For the comparison, I ported it manually to Mill. There's some we have some automation now to help port things, but this one was done manually. So this is on the right we have the Gradle config for the Mockito error prone submodule. This is just one of the arbitrary modules within the Mockito code base. On the left we have the Mill build config for the Mockito error prone submodule. So the first thing we realize is that they look almost exactly the same, and that is because whether you're using Mill or Gradle or Maven or Bazel to build this module, it just happens to need these flags, it happens to need these dependencies, and Mill or any other build tool will need to provide this configuration to make it work. The syntax is a bit different because Mill uses Scala syntax rather than Groovy you see on the right, but it's basically the same thing. Where things differ is that where Gradle is configured using these global mutable variables that you kind of just mutate and therefore do not get good ID support because that's how global mutable variables work. Mill is configured using method definitions, using DEF in its Scala syntax, and overrides. So IntelliJ knows this is an override. IntelliJ can show this little icon here showing the upstream members that methods it's overriding. So if you're wondering, what does forkargs do, which is a reasonable thing to ask, not only can you ask for the documentation, which you can also do in Maven or Gradle, not only can you go to ChatGPT or Google, you can also just go to its overridden implementation. You can see what value was there before. In this case, it was an empty sequence before of strings. Again, this is Scala syntax, so it might be slightly foreign, but hopefully not too confusing. It's an empty sequence of strings. And I can kind of find usages here just to see where this gets used. So I can see that forkargs gets used in this runner task. Runner gets used in run background and run fork task. Run fork task gets used in run. So what's interesting here is that this is kind of the workflow you're used to every day working in Java code bases with your IDE. You navigate around, no documentation, no problem. Just jump to definition, find usages, you can generally figure out what's going on. So if everything's working perfectly and you don't need to touch your build or you've already memorized everything you need, it's not interesting. But when things go wrong, some plugins not doing quite what you expect, two plugins are not working well together, your own customization is having problems, this becomes very valuable. It makes your build no longer a black box, but rather just another code base you can jump around, just like the Java, Kotlin, or Scala code you use in your application. So I showed you navigating downstream in your IDE. You can also navigate upstream. Like, let's say I don't know what this final main class thing is, and let's say there's no documentation. Well, I can jump to it. You see that there's no documentation. In Maven or Gradle, you'd be stuck. But in Mill, we have implementation. And we can see it basically delegates this final main class optional thing. If there's one, it provides it. If there's an error message, it fails. Okay, we don't know what this is. Maybe we jump to that. Again, no documentation. Again, we have the implementation. So we can see that we call main class, which is any explicitly specified main class. If there is one, we use it. If there's none, we then call all local main classes, which uses this class graph library, another open source project, to scan your class files looking for public static void mains. If there's none, we raise an error. If there's one, we use that. If there's multiple, we have a different error saying we have multiple, please tell me which one you want to run. So even though not everything is perfectly documented, which is the case in any real world code base, and you're not kind of limited by what you can Google or copy paste of Stack Overflow or generate using your ChatGPT. Rather, you can just explore the code base and navigate it just like you do any application code, using the same IDE, using the same jump to definition, find usages, and so on. And you can understand what your build is doing rather than having it be some impenetrable black box that only experts or build tool plugin authors can figure out. So that's the ID support angle. So even though mill is much a smaller project than Maven or Gradle, because it's configured using methods, method calls, classes, and inheritance and overrides, these are all things that IDEs are very good at navigating, whereas traditional build tools like Gradle and Maven are generally configured using global mutable variables, which IDEs, no matter how smart, have much more trouble finding their way around. Okay, so the last thing to talk about here is the programmability angle. I think the most interesting thing to mention here is that where most build tools require extensions to be published as plugins. So if you want to write your own Maven plugin, you have to go look up the Maven Mojo API and figure that out in addition to whatever logic you want to write. Even to write the Gradle plugin, similarly the Gradle plugin API, or now I think you have like 4 or 5 different Gradle plugin APIs to choose from. Mill's interesting in that there are plugins, but in the absence of plugins, or if there's something that the plugins don't do, you can just write code and use libraries to do the thing rather than having to wrap in this plugin ceremony. So just to show you what that means, let me set up my workspace. So on the right, I have the kind of minimal viable mill build set up. You see I have object foo extends Java module. That means the foo subfolder has Java code in it, and there's no config because I'm just using all the defaults. So similar to Maven or Gradle, it's convention over configuration. You want to use the conventions, there's nothing to configure. Just leave it. But let's say I do want to configure something. Let's say I want to count the lines of code in this module and write it to a resource file like we saw earlier with Maven or Gradle. How do you do this with mill? So with mill, tasks are just custom build tasks are just method. Every build task is just a method, so custom build tasks are no different. And methods are defined using def. So def, I can do say def line count is a task. And within this task, I can call other methods, which are also tasks. So I can say foo dot sources. If you're not sure which method you want to call, you can look at ask your IDE, it'll tell you. You can also jump to definition, it'll show you what the implementation is, so you're never lost. And let's say I want to map it. For each file, I want to read the lines of that file and get the size and sum them up. So again, this is Scala syntax, so it might be slightly different from the Kotlin or Groovy syntax you use in Gradle, but hopefully you can kind of look at this and more or less guess what it means. And that's all I need to do to define a custom task. It's just a method that has this task wrapper around it. So now I can do mill show foo.line count. So once that's done, you see it print 17. First time it needs to recompile might be a bit slow, but subsequent recompiles are quite fast. So this example application has 17 lines. I can do mill inspect foo.line count. You'll see that it automatically captures things like your Java doc, so you don't need to put in a string somewhere. We capture the inputs of upstream tasks that you call, so you don't need to add an explicit depends on clause. These are all these nice quality of life features. And basically, this method that calls another method does some processing it on the value and returns it. The return keyword is optional, and I have my custom task. So what I haven't done yet is I haven't wired it into my resources. So in mill, resources are a task like everything else, and the tasks are methods. And the way you customize methods is by overriding them. So I can say override def resources. Again, you're not sure which one you want to override, you can ask IntelliJ. IntelliJ will happily give you docs and other things. Let's say I want to keep my super so my resource folder doesn't disappear. And let's say I want to use os.write to this task.destination folder, which I'll explain in a moment, my line count as a string. I'm going to append this to my, a reference to this folder to my resource path. So what's this task destination folder? So the problem this solves is that in any build tool, the file system is the world's biggest global mutable variable. You have this target folder. Anyone is reading from anywhere, and anyone's writing all over the place. You don't know who's writing where. 2 plugins happen to use the same folder name, and you'll start stomping over each other's files. It's generally a big mess. Like, you can't safely parallelize things because there'll be race conditions on disk, not just in memory. You can't safely delete things because you don't know who's using the thing that might be deleted, and the task can't automatically recompute things because the tasks don't know what outputs that they themselves generate. So there are solutions to this. You can see in Gradle we have to register inputs and outputs and stuff manually. And the approach Mill takes is rather than saying that, okay, I'm going to write somewhere and I'll tell the build tool, Mill does opposite. Mill says the build tool will tell you where you can write. And where any task can write is this task.destination folder that's unique to every task. So if I do mill show foo.resources, you'll see that I have both foo.foo/resources, which is the super resource folder, because I overrode it, but I kept it around. But I also had this in the output folder, out/foo/resources.dest. So this is the unique destination folder every task is given that will never collide with any other task. So this turns the file system from this global mutable file system to this locally mutable file system that only my task can write to, but globally immutable where other tasks can only read from. And this makes things much easier for both humans to figure out what files belong to who. Just look at the file system path and say, okay, this file belongs to this task. Like foo.foo/resources.dest must belong to foo.resources, doesn't belong to anyone else. It also makes things much easier for a build tool to manage, which we'll see later. So now I can look at if I look at out foo resources.dest, I can see my line count.txt file with 17 in it. And I can do mill foo.run, and you can see my application code can use this resource file generated at build time at runtime. And what's interesting here is that if you look at the code here on the right, you don't see any plugin API, build tool API, or anything. You see objects extending class. You see I'm defining a new method that calls another method and does some processing on it. I'm overriding a method, I'm calling super, and I'm also calling another method, and so on. So this is very kind of vanilla object-oriented code 101, whether you're writing Java or Kotlin or Scala or Python or JavaScript even nowadays, you probably are familiar with these patterns. And just by writing these object-oriented code, you're able to configure your build tool to do whatever you want. In this case, counting lines and putting them on your resource path. So let's take this one step further. Let's say that instead of writing a resource file, I want to write a HTML file as my resource. So this is just, again, an artificial example, but let's say I want to use a third-party library, which is common. How do I use third-party libraries in my build? In most build tools, you need plugins. In Mill, if I want to use, for example, Thymeleaf, which is a popular HTML rendering library, it doesn't come bundled with Mill because Mill is not a web framework. If you try to use it from the command line, you'll see my terminal yells at me, just like my IDE is yelling at me here. But what Mill does let you do is it makes it very easy for you to kind of add dependencies for your build in this header syntax, similar to what we saw for JBang earlier, where I can say the Maven deps includes com thymeleaf 3.1.1.release. And now if I reload my build, it'll hopefully work. I can run foo.run here. So I think I need to say I think it's org.thymeleaf. Okay, now that's happier. Let's see if this one is happy. This one's not happy. Might have to restart the IDE. Sometimes the IDE integration is not perfect yet, so there's still some hiccups. So hopefully this will be happier now that I've restarted. Come on, IntelliJ. Okay, now it's happy. So you can see now I've managed to get IntelliJ to cooperate. I can jump to Thymeleaf, see it available in my IntelliJ external libraries list. I can import things from Thymeleaf, like I want to import the template engine, I want to import the context.context. And I can start using this, like def HTML snippet as a new task. Oops. Try to make this a bit bigger. And then I can call, let's say, var context equals new context. Context dot set variable line count as line count. and then new template engine dot process. Let's copy the template from the slide because it's a bit long. Here's my template. Process this template with my context. So now I can do mil show foo.html snippet. You can see that it recompiles the build and it generates this HTML at build time using timeleaf. I can look at the file on disk as well. So if I open up out/foo/HTML snippet, in this case it's a JSON output because it's metadata rather than file system. You can see that I have the serialized string in JSON together with some information so Mil knows how to invalidate it if the inputs change. And if I wire it up to my resources, I can do foo.run, and you can see we are now using this HTML that we generated at build time using a third-party library in our runtime resource path from my application code. So this example again is a bit contrived. No one's actually going to render the line count as a HTML file to use at runtime. That's a bit silly. But it just shows how easy it is to use these third-party libraries. There is no mil line count plugin. There is no mil HTML rendering plugin. Instead of that, you can just write normal code or even use the third-party libraries themselves rather than relying on some wrapper foo plugin that is usually less maintained than the foo library itself. Like in this case, I want to render HTML using timeleaf. Timeleaf is a perfectly good library, has great documentation, good APIs and everything. I can just use the real timeleaf rather than trying to find someone to wrap timeleaf in some build-compatible plugin for me. So that's the programmability angle. So although all build tools are programmable, Mil tries to make programmability much easier and much more familiar than others. So if you know how to write Java, Scala, Kotlin code, use Java, Scala, Kotlin libraries using your normal IDE, Mil lets you use all of that together with things like autocomplete, jump to definition, imports, and everything. It all works in your build just like it does in application code. And you can write code that looks very natural rather than using some special build tool plugin API. So that's why I think Mil is interesting. Still a young project. As you saw, the IDE support's not perfect. I had to reload my IDE to get it to pick up the change in dependencies. But hopefully there's a lot of interesting things here that other build tools haven't managed to achieve. I think one of the reasons why Mil is able to achieve this is it builds upon this idea of object-oriented builds that, as far as as I understand, is pretty unique in this build tool solution space. So, what are object-oriented builds? Earlier we talked about how every build tool needs to define templated graph computations. And templated graph computation engines are very complicated. If you or me try to define like a class that models a templated graph computation engine, it'll be a very complicated class. It'll be hard to learn. It'll probably be buggy. There'll probably be many iterations of it over the years. But it turns out that there is kind of a standard way that everyone's already used to defining templated graph computations, and that's object-oriented programming. You've all been using this for years or decades at this point. And this is object-oriented programming turns out to perfectly model the templated graph computations that most build tools need to work with. So for example, earlier we saw object foo extends Java module. You know how objects extending classes work. So you know that when I extend a class, I get these methods. Methods call each other and pass data. So sources get returned, something gets used by compile, return something gets used by class path, and so on. This is all very standard. I inherit the class, I get all its methods, including the call graph. If I define a new method like line count that calls all source files, or I override a method like resources and call super resources and also call line count. These aren't trivial concepts, and many students struggle with this in school, but they've already struggled with it and learned it, and now that they've learned it, they already know immediately how this will affect my call graph without me having to teach you anything. So every build tool needs to do this, but with Mil, because you're using overrides and supers, you already know how this works. There's no new API for you to learn. And if I want to template this, I turn my singleton object into a class or interface. In Mil, it's called trait, but it means the same thing. It's basically a class or interface you can instantiate multiple times. And I instantiate it multiple times, and I have templated my graph. And everything you expect works. I can override things in each object, singleton. I can have subclasses that override things and instantiate the subclass multiple times. All the standard object-oriented design patterns work here. and you already know how to use them to kind of model this complex, non-trivial templated graph. Like even in this case, I have this templated graph here with 2 modules and a bunch of stuff in it. But if you look at the code on the left, it should hopefully be very familiar to you, even if you've never looked at Mill before. You have objects extending classes, classes extending other classes, and methods that call each other and override other methods. And once we have this graph, Mill can then take over and do all the build tool stuff. So for example, Mill can see that compiler and line count do not depend on each other and therefore can run in parallel. But assembly depends on both, and so assembly needs to wait for the 2 earlier things to finish before assembly can start. Mill can see that every method has a fully qualified name that we can use not just in the code when we call, like, for example, line count here, but we can also use it to call foo.line count from the command line. And can also use it to assign each task unique places on disk to put their stuff that will never collide. For example, foo.compile gets foo/compile.json for its metadata and foo/compile.dest for its file system output. And it will never collide with assembly.json and assembly.dest. And Mill can do automatic invalidation for you. So if you touch your resource folder and add a new resource file, Mill can just do a breadth first search, see that resources in assembly are downstream, so assembly needs to recompute. Compile and line count are not downstream, so compile and line count do not need to recompute. Mill knows where the previous output for compile and line count are because they are in the standard location at compile.json, compile.dest, so you can reuse them. And Mill knows where the previous output for assembly is because also at a standard location, so you can go delete it on your behalf and recompute it. And what's most interesting here is that Mill does all this without any code in your build config related to dependency tracking, parallelism, or caching. So you write kind of vanilla object-oriented code, object extends class, method calls other method, override super, all the standard O things. You do not write depends on clauses for tasks or inputs or registration patterns. You do not write like threads of mutexes or semaphores or locks. You do not write cache key computations and cache invalidation logic. Mill does all that on your behalf at 99% of the time, unless you're doing something really unusual. And you can just write vanilla object-oriented code here to configure your build. So earlier we saw that build tools need to do a lot of things, and Gradle is complicated because it needs to do all these things that your build tools need to do. Mill also needs to do all these things, but Mill manages to cram it all into a much smaller object-oriented kind of model. So like how are tasks run from the CLI? Well, we have methods have names, so we use a method name. How do you define custom tasks? In Gradle, there's this task.register, task.define, and so on. In Mill, you define a method, and that's a custom task. So all of these things do have answers in Mill. It's just that these answers fall very nicely into this object-oriented programming model that you hopefully will be very familiar with. So just to wrap up this idea, so in Mill, builds are just methods, objects, and classes. Extends, override, super work exactly as you learned in Java 101. They also work exactly as how IntelliJ expects. That's why IntelliJ was able to navigate around the Mill build so easily, including things like jumping to overridden methods and following downstream, upstream, your method call graph. And Mill handles everything else for you, all the build tool stuff most of the time. This has advantages. For example, you always get good performance because you don't have plugins forgetting to cache things or forgetting to turn on parallelism like you do in other build tools. You don't need to clean because you don't have plugins screwing up the cache key computation most of the time. Most of the time, Mill handles it for you, and then you'd have no chance to screw up. And just makes life easier for everyone. So that means that people like me working on Mill have time to do things like Chrome profiles or selective testing rather than struggling with these graph computations. Can do a lot of tooling integrations because integrating tools is easy. Like we saw earlier, integrating Timeleaf was easy. And for you as a build tool user, you can spend less time futzing with your build and more time working application code you care about, hopefully. So on the topic of build tool integrations, because it's easy to integrate build tools, we've taken the liberty of integrating like all the open source build tools in Mill that I could find. Not all, but most of them. So like all the linters for Java, Kotlin, and Scala, all the formatters for Java, Kotlin, and Scala, code coverage, all the different web frameworks, all the different packaging formats, different publishing targets, all your annotation processors, and even things like Android and experimentally, we've just already integrated, so there's docs on how to use integration. Some of these are third-party plugins that you can use, And if something is not that you need is not integrated and not in the plugin that's available, you can just integrate it yourself, like how we integrated Timeleaf earlier. You just import it in your build and use it programmatically via its API. So that's the idea of object-oriented builds. I think that's why Mill is able to do all these things. Like Maven and Gradle have been trying to improve the ID support for 20 years. They have been trying to improve their programming model. But despite that, it's pretty complicated because these graph computations are not easy. But with this idea of object-oriented builds, we're able to squeeze the complexity of these graph computations into an object-oriented programming model. And from there, it makes it much more familiar to anyone who's ever learned Java 101 in school. And so anyone, whether it's me as a Mill maintainer or other people who are using Mill, are able to modify and customize a Mill build much more easily than Maven or Gradle. So this is the last slide. Hopefully this talk was interesting to you. I won't read this out, it just summarizes everything we talked about. I guess the long and short of it is, if any of you have ever wondered, like, why is Maven or Gradle so complicated and is there a better way, I encourage you to give Mill a try. It's definitely a much younger project. As you saw, the ID support still has a few bugs, and it doesn't have 20 years of battle testing that Maven or Gradle do. But a lot of interesting ideas. They're not just theoretically interesting, but feed into concrete user-facing improvements. Things like better performance, things like much better ID support, or things like much easier programming. So if you want to customize your build, it's much easier for you to do. So the website again is millbuild.org, mill-build.org. There's docs for getting started with new projects in Java, Scala, and Kotlin. All the examples are downloadable, so you can download them, unpack the zip, and run it directly on your laptop. It should work. These are part of our integration tests. And there's some migration instructions as well. So if you want to migrate an existing project, there's like time estimates on how long some other migrations took, and how to use automation to help make the migration easier. So that's the end of the presentation. I hope I can take questions. Thank you.